So this is a video explanation of number 3 from the Newton second law practice problem worksheet. In this problem we have a rock on an incline. We have an incline that looks like this. There's a rock sitting on it. We're given two pieces of information. We know the mass of the rock is 5 kilograms. And we know the angle of inclination is 20 degrees. So this is 20, and we know the mass of the rock. We have a list of 5 things we need to do. First off is drawing a force diagram. Now recall that when we have an object on an inclined plane, we want to consider the forces in a rotated axis, meaning because the rock moves along the inclined plane, so the rock moves this direction parallel to the plane, I want the axis to follow that direction. So I'm actually going to put an axis for my picture that looks like that. Let's try that again. In fact, on the worksheet diagram, the axis was already drawn for you. This would be our x direction, and the y direction will be perpendicular to that. So that would be y. Now I can start drawing forces. The first force we know we have is W. We always have weight. And weight is always going to pull straight down. There's also support force because the rock is sitting on an inclined surface. And so the support force is going to be perpendicular to the surface. Now, this diagram looks a little messy. It's kind of hard to see, so I'm actually going to scroll down here, or scroll over here, and redraw this. We have W going down. Let's a little more. W going down, and the support force going up at an angle like that. And our axis runs like that. Give me 1 sec. Sorry, try and get this axis in cleanly. There we go. Now, so actually my force diagram at this point, you could leave it like that. It's done. I've drawn all the forces. We don't have friction. There's no push or pull. Just support force and weight. So that's really our answer to A. However, in B, you're asked to go ahead and then include the x and y components of W. So the x and y components of W, I'll draw them in different colors. The y component will be this line. So that would be WY. The x component, how do you feel about purple? We'll go purple. That would be W in the x direction. So the purple actually gives us our answers, the green and purple I should say, give us the answers to B, include WX and WY. Now, we're actually now asked to start doing some calculations at this point. And the first calculation that you're asked to do is to calculate the net force in the x direction. If I look at my diagram, the only force that's acting in the x direction is Wx. So when I say calculate the net force in the x direction, really what you're being asked to do is calculate Wx. So if I go back to my diagram, I have to think about the angles that I know. This angle here is 20 degrees, which is going to make this angle here be 20 degrees. You can see your class notes for that. The quick version is I actually have a right triangle right here, which makes this angle here 70 degrees, which is how I know that this angle here is 20 degrees. So now that I know that angle is 20 degrees, I can determine that weight in the x direction is equal to weight times sine of 20 degrees. Yes, this sometimes throws us for a loop because I'm saying an x component is based off of a sine function, not a cosine function. That is okay, we have a different angle for definition. Now before I'm done, I need to remember that weight can be determined using mass, because weight is the same as mg. And now I'm ready to calculate the net force in the x direction. We were given the mass is 5 kilograms. I know the value for g is 10 meters per second squared. I am not putting in negative because I've accounted for the direction in my force diagram. I'm calling this in the x direction. It would be strange to label it as negative 10 since it's pulling in the x direction, so we leave the negative out. Times sine 20. So 50 times sine 20. Let's see what that gets us. Yep. 17.1 newtons. This is in the x direction. So that's the answer to C. So that means this rock is being pulled down along the incline with a force of 17.1 newtons. So this is the force that pulls the rock down the incline. In part C, you're asked to calculate the acceleration from that force. This is pretty straightforward. Calculate the acceleration of the rock down the incline. Remember, if we know a force on an object and we know a mass, we can calculate the resulting acceleration. So really what I'm asking for here is AX. That's going to be the net force divided in the x direction divided by the mass. We just calculated that net force at 17.1 newtons. The mass was 5 kilograms. So I get 3.42 meters per second squared is the acceleration down the incline. Interesting to note, this value is g sine theta. That will always give you the acceleration down a frictionless incline. Frictionless is important here because if we had friction, our force diagram would change, our net force value would change, and the acceleration would change. The last question, I guess I'm actually up to E. I think I must have misnumbered. This last part was D. In the last question, E, you're asked, what is the force needed to keep the rock at rest? This is conceptual. If the rock stays at rest, we can conclude we know that the net force in the x direction is 0. Or friction must balance weight in the x direction. Or friction would have to equal 17.1 newtons. Essentially what I'd be saying is, if this was my force diagram, W, support force, there would be a frictional force going up this way that equaled that value Wx. And they would cancel out and cause no net force in the x direction. This is the end of number 3 from Newton's second law of practice problems.